Assalamu alaikum. Welcome to lecture 19 of CS 218 Data Structures and Algorithms. In this lecture, we start the topic of trees. Chapter 13 of Book 1 is used as reference. The tree structure. A tree structure consists of nodes and edges that organize data in a hierarchical fashion. The data elements are stored in nodes, and pairs of nodes are connected by edges. The directed edges represent the relationship between the nodes that they link together. The edges are directed downwards. Formally, we can define a tree as a set of nodes that either is empty or has a node called the root that is connected by edges to 0 or more subtrees to form a hierarchical structure. So this is a tree with 0 nodes. In the definition, we say a tree is a set of nodes that either is empty. So this is a set of nodes that is empty. So this is a tree. What about one node? This node will be called the root, which is connected to 0 subtrees. So by definition, this is also a tree with one node. Now there are 6 nodes. This is a tree. The uppermost node is the root, and then there are 3 subtrees that are connected to the root. The leftmost subtree is of one node. The rightmost subtree is also of one node. The middle subtree contains 3 nodes, one of which would be its root of the subtree. And then this root of the subtree in the middle, is connected to 2 more subtrees. So each subtree is itself a tree. Let me show you some examples of trees. Family trees are tree structures that depict the relationships between different generations in a group of people related by blood or marriage. A classic example of a tree structure is the representation of directories and subdirectories in a file system. A file system is essentially a tree. The topmost node of the tree is known as the root node. It provides the single access point into the structure. The root node is the only node in the tree that does not have an incoming edge. The root of this tree is T. The other nodes in the tree are accessed by following the edges from a starting node to a destination. The nodes encountered form a path. The length of a path is the number of edges that form it. The sequence T, N, R, and K forms a path from T to K of length 3. Every node except the root has a parent node, which is identified by the incoming edge. A node can have only one parent, resulting in a unique path from the root to any other node in the tree. X is the parent of both B and G. Each node can have one or more child nodes. The children of a node are identified by the outgoing edges. All nodes that have the same parent are known as siblings, but there is no direct access between siblings. T has three children, X, C, and N. But if you are at X, you cannot go to its sibling C directly. First, you will have to move to its parent, and from the parent, you can go to any other child. Nodes that have at least one child are known as interior nodes. Nodes that have no children are known as leaf nodes. The interior nodes are X, C, N, G, and R. Notice that I am not naming the root as an interior node because that is the root. The root will not be counted in interior nodes. The, the leaves are B, J, Z, K, and M. A tree is a recursive structure. Every node can be root of its own subtree, which consists of a subset of nodes and edges of the larger tree. T has three subtrees rooted at X, C, and N. This is the subtree rooted at X. This is another subtree rooted at C. And this is the third subtree rooted at N. The descendants of a node are its children and their children all the way down to and including the leaves. Every node in the tree is a descendant of the root node. The descendants of X are B, G, and Z. The ancestors of a node are the nodes along the path from the root to itself. The root node is the ancestor of every node in the tree. The ancestors of R are T and N. One of the most used trees in computer science is the binary tree. A binary tree is a tree in which each node can have at most two children. So a node can have 0 children, a node can have one child, a node can have two children, but not more than two. One child is identified as the left child and the other as the right child. In the remainder of this discussion, we focus on the use and construction of the binary tree. This is not a binary tree. Why? Because T has three children, which goes against the definition of the binary tree. Any node that violates this definition will render the whole tree non-binary. So this is not binary, but this is a binary tree. You can see that each node has at maximum two children. Let us talk about binary trees in detail. Three different arrangements of 9 nodes in binary trees are shown here. The nodes in a binary tree are organized into levels. The root node is at level 0 with its children at level 1. The children of level 1 nodes are at level 2 and so on. So if the level of the parent is k, then the level of the child is k plus 1. The depth of a node is its distance from the root. A node's depth corresponds to the level it occupies. So in tree A, the depth of G is 2. In tree B, the depth of G is 3. And in tree C, the depth of G is 6. The height of a binary tree is the number of levels in the tree. The last level in a tree of height h is h minus 1. The first level is 0. The last level is h minus 1. So total number of levels are h, which is the height of the tree. The height of tree A is 4. The height of tree B is 6. What is the height of tree C? 8. The width of a binary tree is the number of nodes on the level containing the most nodes. The width of tree A is 4. We are looking at the most populated level, which is level 2. The width of tree B is 3. Again, level 2 is the most populated. The width of tree C is 1. No matter what level you consider, each level has just one node. The size of a binary tree is the number of nodes in the tree. The size of all three trees shown here is 9. A binary tree of size n has a maximum height of n when there is one node per level. Can you see any such tree here? Yes, you are right. Tree C has the maximum height. See, the number of nodes in each of these trees is the same. However, in tree C, each level has just one node. So it has the maximum height possible with 9 nodes. A binary tree of n nodes will have the minimum height when all possible slots in it contain nodes and no slot is empty. In this picture, I show you all the possible slots that are available for node placement. The shortest tree will be obtained when none of the slots is empty. Every one of them contains a node. Consider this table. In the 0th level, there is only one slot for a node. So this is 2 to the power 0. Level number 1 can accommodate 2 nodes or 2 to the power 1. Level number 2 can accommodate 4 nodes or 2 to the power 2. So if the tree has a height h, then the last level will be h minus 1 and it will be able to accommodate 2 to the power h minus 1 nodes. I hope that you follow me so far. From this table, if I have a tree of height h, then the total number of nodes in this tree will be found by adding the number of nodes in each level, and that's what I do. This is a finite increasing geometric series. Do you remember the summation formula? The first term is 2 to the power 0. The ratio is 2 and the total number of terms here is h. So the formula for summation is a bracket open r to the number of r to raise to the number of terms minus 1 bracket closed divided by bracket open r minus 1 bracket closed. That formula I have used over here. And in a binary tree of height h, the maximum number of nodes is 2 to the power h minus 1. This is the number of nodes when the height is h. This can be written as 2 to the power h is n plus 1. I apply log to the base 2 on both sides of the equation. And when all possible slots contain nodes and no slot is empty and the size of the tree is n, then the height of the tree is h equals log of n plus 1 to the base 2. This is the minimum height of the tree. Now I will talk about different kinds of binary trees. The first on my list is the full binary tree. A full binary tree is a binary tree in which the root and each interior node contains two children. This is also called a strictly binary tree. We use the acronym SBT for the strictly binary tree. I will mostly refer to it as the strictly binary tree. I believe that the name strictly binary conveys more information than the name full binary. In this tree, a node can have two children, a node can have zero children, but it cannot have one child. So I show you three examples of full binary trees or strictly binary trees. And you see that here the leaves are obviously those nodes which have zero children, and all the other nodes in these trees contain exactly two children. Then we have something known as the perfect binary tree. A perfect binary tree is a full binary tree in which all leaf nodes are at the same level. The perfect tree has all possible node slots filled from top to bottom with no gaps. We use the acronym PBT for the perfect binary tree. So, if you remember the formula that we just worked out, that formula was actually for a perfect binary tree. It gave us the number of nodes in a perfect binary tree of height h. So you can see that in a perfect binary tree there are no gaps. If you want to add a node to this perfect binary tree, you will have to start a new level. Then we have something called the almost complete binary tree. A binary tree of height h is an almost complete binary tree if it is a perfect binary tree down to height h minus 1 and the nodes on the lowest level fill the available slots from left to right, leaving no gaps. The book calls this tree a complete binary tree. But I think that the name almost complete, which is used in other literature, conveys more information. We use the acronym ACBT for the almost complete binary tree. If you look at these trees and for some moments ignore the last level, then you see that above the last level, these trees, both of them, they are perfect. Now, if you look at the last level, you see that the first slot is filled, the second slot is filled, the third slot is filled in the left tree, and now we are going to fill the fourth slot. So whatever filling we have done of the tree so far, we have not left any gaps. And the same is true for the right tree. The first slot is filled in the last level, then the second slot is filled with Y in the last level, and now we are going to fill the third slot. So when a tree is filled in such a way that up to the point where it contains nodes, there are no gaps, then this is an almost complete binary tree. The left and right subtrees of the root of an ACBT differ in height by 0 or 1. Every PBT is also an ACBT. So here you see a perfect binary tree, and this is also an almost complete binary tree. Why? Because this follows the definition I just gave you. Look at the root. Now look at its left subtree. What is the height of the left subtree? There are 3 levels in the left subtree. The height is 3. Now look at the right subtree of the root. What is the height of the right subtree? There are 3 levels in the right subtree. So the height of the right subtree is 3. Now if you take the difference of heights of both subtrees, 3 minus 3, the answer is 0. So this is a perfect binary tree, and this is also an almost complete binary tree. If we add another node to a perfect binary tree in the leftmost available slot, it ceases to be a perfect binary tree, but it still remains an almost complete binary tree. So after this addition, we don't have a perfect binary tree. But now if you look at the left subtree of the root, the height is 4. And if you look at the right subtree of the root, the height is 3. And left minus right, 4 minus 3, the answer is 1. If you are using this definition of the almost complete binary tree, it is important that you always minus the right subtree from the left subtree. Minus the height of the right subtree from the left subtree, not the other way around. What I'm trying to say is if the difference in height is minus 1, then it's not an ACBT. The difference in height has to be 0 or 1. So the number from which you are subtracting is the height of the left subtree, and the number that you are subtracting is the height of the right subtree. If a node is added, leaving empty slots between the new and existing nodes, the tree ceases to be an ACBT. Look at this addition that I just made. I left out quite a number of slots and then I added another node. Now this tree is not an almost complete binary tree. An almost complete binary tree is always filled in such a way that up to the last point or up to the last node there are no gaps. Types of almost complete binary trees. This is type A. This is actually a perfect binary tree. I just told you that every perfect binary tree is also an almost complete binary tree. This is the second kind of ACBT. Now, the difference in height of the two subtrees of the root is 0. Height of the left subtree is 3. The height of the right subtree is also 3. Concentrate on the left subtree of the root. The left subtree of the root is a perfect binary tree. Now concentrate on the right subtree of the root. If you look at it, you will see that the right subtree is an almost complete binary tree. Here we have completely filled the left subtree in the last level, and now we are filling up the right subtree in the last level. So the second kind of ACBT is formed when the difference of height of both subtrees is 0, the left subtree is perfect, and the right subtree is almost complete. This tree is the third form of ACBT, tree C. The difference in height of the two subtrees of the root is 1. Height of the left subtree is 3. Height of the right subtree is 2. Left minus right, 1. Concentrate on the left subtree of the root. This is an ACBT. Now concentrate on the right subtree of the root. This is a PBT. Here we are filling up the left subtree in the last level. So the third kind of ACBT has a difference of height equal to 1 for the two subtrees of the root. The left subtree is an ACBT and the right subtree is a PBT. So when is a binary tree almost complete, you ask? If the tree is a PBT, the tree is almost complete. If the difference in height of the two subtrees of the root is 0, the left subtree is a PBT and the right subtree is an ACBT, the tree is almost complete. If the difference in height of the two subtrees of the root is 1, the right subtree is a PBT and the left subtree is an ACBT, the tree is almost complete. I have a few tasks for you here. I hope that you find them interesting. Task number 1 is draw all possible ACBTs for 7, 11 and 13 nodes. Do you have more than one trees for each case? Task number 2, draw an ACBT which is not an SBT. Task number 3 says draw an SBT which is not an ACBT. Task number 4, draw all possible perfect binary trees of size n such that n is between 16 and 65. Task number 5 says consider trees of 0 and 1 nodes. Is the considered tree a perfect binary tree, an SBT or an ACBT? Task number 6 says draw an ACBT and an SBT of 2 nodes. Save your snapshot as my roll number _ lecture 19. and submit your response in the assignment titled Lecture 19 Tasks in Google Classroom. So what did we learn today? We were introduced to the tree structure. We learned about the terminology associated with trees. We learned about the binary tree, and we learned to classify binary trees. Things to do for you. Read the book. Submit your answers to the tasks in this lecture. Note your questions and put them up in the online session. And email suggestions on content or quality of this lecture to me. Take care. Allah Hafiz.